In this chapter, we are going to be talking about our carboxylic acid and ester functional groups. The learning objectives for this chapter are similar to our other learning objectives for our previous organic chapters. We're going to start off by talking about the different functional groups, naming rules, then we'll get into physical properties and chemical reactions that these functional groups undergo. Let's start off by identifying our carboxylic acid and ester functional groups. When we talked about our aldehydes and ketones, we talked about how these were aldehyde and ketones were part of our carbonyl functional groups. So the carbonyl functional group is a generic term for any functional group that features the C double bond O in it. There's ketones, which have the C double bond O with a carbon on either side. Aldehydes have the C double bond O with one carbon and one hydrogen, or at least one hydrogen. That's the distinguishing feature. And then amides have the C double bond O and this NH2 group that will be in our next chapter. But for now, we're going to be focusing on our carboxylic acids and our esters. Esters have a bond to an O, and then that O is attached to an R group, so a carbon something or other. So some students think that this looks kind of like a ether, but it's not an ether because it's attached to the same carbon as this C double bond O. A carboxylic acid has what looks like an alcohol attached to the C double bond O. This OH here makes this acidic group because the hydrogen here can detach from the oxygen way more easily than this H can from that carbon. So this H can detach in solution, making this functional group acidic. There's a special name for carbonyl functional groups that have a nitrogen, oxygen attached to them, or a halogen. These are known as acyl functional groups when you have a nitrogen, oxygen, or one of the halogens attached to the C double bond O. So acyl is a generic term for a carbonyl functional group with a nitrogen or oxygen. We're not going to be talking about the halogen acyl groups. That's a different OChem class that we'll have to worry about those. So when we're trying to look at molecular structures to identify our acyl functional groups, we can see that we have this ester functional group in propyl acetate, which is responsible for the scent of pears. Oxalic acid is found in spinach, and it has two carboxylic acid functional groups bonded together. Capsaicin, which is responsible for the peppery flavor of spiciness, spicy peppers, that has an amide functional group in it. Esters are usually responsible for some odors that are very pleasant, and then carboxylic acids are, of course, esters. So how do we write condensed structural formulas for these new functional groups? Well, you can always just draw out that functional group. Remember, you can't. It still counts as a condensed structural formula as long as you aren't drawing the individual bonds to those hydrogens. So we can still write CH3 for terminal groups, and then draw out double bond O, and then an O, and then CH2, CH3. Alternatively, you might see, instead of the C double bond O and then another O, you might see it written like this, with two O's in a row. This isn't normally as clear as that, but this is an acceptable way if you are trying to get it all in one line, like those text boxes on Mastering Chemistry. Next, we have carboxylic acids. Carboxylic acids, you of course can draw out the double bond in the stuff. So you can, of course, go like this and draw out the functional group with the double bonds and stuff. Or you can just write COOH like that. And so this COO means ester. And then we have the COO again, but that COOH is carboxylic acid. Other variations include doing CH3, CO2, CH2, CH3. I don't like that one as much, just personal preference. You can also do that down here with the carboxylic acid and abbreviate it CO2H. Now that we've covered many of our different functional groups, let's practice identifying all the functional groups in aspartame, the artificial sweetener. Go ahead and pause this video, draw out the structure of aspartame on your paper, and try to circle and label all the different functional groups that you recognize. Unpause the video when you're ready to double check your answers. Okay, so right here we have an O, and they're that O and that double bond O are attached to the same carbon, so that's part of the same functional group. This is an ester. This is a phenyl group, also known as, that's phenyl or benzene, aromatic, whatever you wanted to call it. I see a nitrogen here, and that's attached to this carbon, which has a double bond O. So this double bond O and that nitrogen are part of the same functional group. This is an amide, which will be the focus of the next chapter. This is an amine functional group. And then this, since the OH and the double bond O share a carbon, that is a carboxylic acid. A carboxylic acid is not a ketone with an alcohol, it is a carboxylic acid. Just like if you called an ester a ketone and an ether, you would be marked incorrect. An ether is different. Ester is all those things bonded together. Let's think about the structures of our carboxylic acid and ester functional groups. Can carboxylic acids be cyclic? Can esters be cyclic? How about you think about that for a moment? Carboxylic acids cannot be cyclic. They have an OH group to them. This has 2 bonds already. This has 1 bond already, which is the most that oxygen and hydrogen can already have. And this carbon already has 3, so it can only form 1 more. So carboxylic acid functional groups can never be cyclic. Carboxylic acid functional groups are always terminal. They're always somewhere at the ends of your molecule, much like aldehydes were. Can esters be cyclic? Yes. You can have a cyclic ester as long as you have a long enough carbon chain that you can connect these together. So you could connect the ends together by making either a 5-membered ring or a 6-membered ring. So we call it membered rings because not all of the corners are carbon. So you could have a cyclic ester that's a hexagon or cyclic ester that's a pentagon. Let's think about all of our different types of isomers. Can carboxylic acids and esters exhibit skeletal isomerism? What about positional isomerism? Can they be functional group isomers? Go ahead and pause the video and think about your answers to each of these questions, and then unpause the video when you're ready to compare your answers to mine. So for the first one, I'm going to say yes, carboxylic acids and esters can have skeletal isomers as long as that part of the carbon chain is long enough. So as long as this part is long enough that you could rearrange the carbons. Can carboxylic acids exhibit positional isomerism? No, because carboxylic acids are always terminal. And so that carboxylic acid can never be in a different position on your molecule. It always has to be carbon number 1. What about esters? Can esters exhibit positional isomerism? Yes. So the location of that ester group can appear to shift in your molecule. So if I take this and I kind of shift it over to there, then it would look like these two molecules are positional isomers. The position of that ester group appears to have shifted over by 1 carbon. So that's positional isomers. Can carboxylic acids and esters be functional group isomers? Functional group isomers have the same chemical formula but different functional groups. And yes, carboxylic acids and esters with the same number of carbons will have the same molecular formula. So if I take I'm going to try to draw out one that has a few different. So here's my carboxylic acid version that had 3 carbons to it. And so if I shift that C double bond over 1, then I can take this CH2 and kind of shove it in there, and now it becomes a CH3 group, and so that CO gets shifted over. And so those are functional group isomers. They will have the same molecular formula. Look at the structures below. What types of isomers are these? Go ahead and pause the video, identify the relationship between these two molecules, and unpause the video when you're ready to check your work. Okay, so both of these are esters. And so that can't be functional group isomers because they have the same functional group. They are not carboxylic acid, so we can eliminate those. And so our options are skeletal isomers versus positional isomers. Skeletal isomers have a different arrangement of the carbon skeleton, so the carbons that are connected together have to be arranged differently. So that doesn't really make a lot of sense. These are positional isomers. The ester appears like it's shifted over by 1. I think this is also the same as what I just drew on the previous slide. Yes, that is exactly what I just drew on the previous slide. Woo!